On behalf of our college management, on behalf of our department, and on behalf of our HOD, and on behalf of all the coordinators of this 6 days FDB, we're very much happy to welcome you for the day 2, session 3 of this 6 days online faculty development program sponsored by Actors. For the third session on the topic Introduction to Smart Grid. Once again, we are very happy to have you, sir, for this session. We would like to have the session with Dr. Vichidi Babu, sir, head of the Department of LC from IIIT TDM, Kanjipuram. Sir, the session is over to you, sir.
Yeah. Thank you very much. Yeah, just enable to share the screen. Is it visible now?
Yes, sir. It's visible, sir. Yeah.
Oh, sorry. Is it visible now?
Yes, sir. It's visible, sir.
Visible, right?
Yes, sir.
Okay. Yeah. Very good afternoon to all of you. So thank you for joining for the second session on Atal MTP. As in the yesterday's session, so I have highlighted the importance of Internet of Things in electrical power and energy systems, and also brief about the renewable energy technologies and energy storage, and overview of smart grid. This all I have highlighted in the previous session. So in this session, I am going to highlight the importance of the grid connection requirements and the standards for solar photovoltaic system. And all of us know that the solar photovoltaic system is a very promising renewable energy source, and it's about 37% of the total installed capacity in India currently, solely made by renewable power generation, especially solar photovoltaic. Right. So with that, a lot of investment has happened with the government of India, and initiated a number of projects, the number of grants, and a number of power plants across India, and they made it. But still, as I told you, that there would be a stochastic nature of the renewable power generations, particularly on solar photovoltaic. Still, we face challenges in integrating with the utility grid. Right. Because you know that the renewable energy sources are usually generated by a private firm and the private companies, and they sell electricity to the government, a particular state. Then after that, the government of Tamil Nadu, for an example, and they sell electricity to the customers. So usually the government has made, they basically, they are the intermediate, or they are the consultant, make the bridge between the customers and the renewable power plant operators or manufacturers. Right. So while selling this electricity generated by renewable energy sources that are done by a private firm, of course, they need certain requirements to sell electricity to the EPR electricity board, because you know these energy sources are intermittent in nature, and the characteristics are very stochastic, and they have a highly nonlinear characteristics between the output and the input. So while selling that, the transmission systems operators or distribution system operator, they impose certain requirements to the power producers, right? That requirements are called the grid connection requirements, right? Because straight away, in the traditional power generation system, the connection requirements are very straightforward, because we have a synchronous generator that is being connected with any turbines. For an example, the hydro power plant, that hydro turbine is being coupled with the synchronous generator, and we are able to produce electricity in the form of alternating current, in the form of voltage and current. And we are able to regulate the output voltage and the frequencies with the help of governor mechanism, as well as with the help of the excitation system. Right. But this is not the case in the renewable energy power generation unit, that the input power is uncontrollable. Because of uncontrollable input power that is being given to any renewable power generator, and obviously it produces a variable output power. That variable output power, in that sense, it's a variable voltage and variable current, and they cannot directly connected with any utility grid, right? So the requirements has to be met so that you are able to successfully integrate the renewable power generations with the utility grid. That requirements are called grid connection requirements. So this is not the new concept. Maybe a couple of decades before the technology was evolving, the connection requirements has been developed by all the countries across the world, and they have their own unique grid connection requirements. For example, a US grid, they have a US grid code compliances, and Canada, they have Canadian grid code requirements. Ireland, they have Irish grid code requirements, and Spain, they have Spanish grid code requirements, and even China, they have a Chinese grid code requirements. Similarly, even India, we follows Indian grid code requirements for integrating solar photovoltaic with utility grid. And however, certain standards to be followed while integrating solar photovoltaic with the utility grid. Yes, what are the standards? Right, and what are all the grid connection requirements? Right, so these all are very important for the researchers or even for the faculty, those who teach renewable power generation to the students as well as while doing research. And this is what the importance of these lectures. Of course, the outline that include the grid connection requirements are solar photovoltaic power system. That the important grid connection requirements that include voltage support, frequency support, the inertias of emulation, and the black start and ramp control. Right. So we discuss each and every point in detail so that you understand the importance of grid connection requirements or photovoltaic power generation system. And understanding that the current energy systems are very centralized power plant and having the power plant that distribute power to the cities, and of course the future power system that would be like completely integrated, right? This is what is called integrated energy systems, having a power plant. And in addition to the conventional or traditional power plant, we have a solar photovoltaic array, we have a rooftop or maybe wind farm or geothermal power plant, or maybe smart grid sensors with control, and we have energy efficient building and the energy storage devices, and we have a plug-in electrical vehicle and the industry, and the system is completely integrated. Right. So of course, as we are reducing the investment risk and optimizing the system in a rapidly changing energy world, we understand that there would be an urgent requirement of new energy technologies and services, and there would be increasing penetration of where renewable energy sources in the utility grid, especially on rural area. You could find there is a huge penetration of wind energy as well as the solar photovoltaic. There would be new communication, the control models in the integrated energy system. That is what we use as energy storage and the plug-in, and electrification, transportation, and integrating energy storage as well. Right. So of course, this component is being well integrated with the future energy system. Of course, the energy market it is playing a very role in promoting renewable energy. Right. So now come to the point in the classical power system, and all know it's a very simple conversion with the help of synchronous generator in the power plant. We are able to generate the alternating current, voltage, and current, and we have a simple transportation, that is the transmission line with a common right of way, and having a simple control mechanism on the power plant itself. And so that you distribute the power to the different customers, including domestic as well as industry customers, and having a distribution system as well. So this completely an AC generation, transmission, and distribution and consumption as well. Right. Always we concern about the equilibrium between the demand and the generation, as it is very much essential to maintain the grid stability in terms of frequency. Right. If there would be a mismatch between the demand and the generation, inherently it causes the changes in the frequency in the grid faces frequency instability. Even sometimes the demand would be huge, so the difference would be huge, that causes the under frequency. Eventually, the grid faces the difficulty of blackout. Right, and this is what always we concern about, making the equilibrium between the demand and the generation, and we need regulating mechanism for both grid frequency as well as a grid voltage. Right, as all of us know that the electric power system and the classical system having a primary energy source. Of course, it's any. I mean, it's depends on the power plant, maybe hydro or maybe thermal or maybe nuclear, and we have the primary energy supplies. Of course, it's a source of mechanical power. then that mechanical power is being given to the synchronous generator, right? Here, this is what the electromechanical energy conversion takes place in a generator with the Faraday's law, and we are able to generate electricity in the form of AC voltage and current. Then further, for economy of operation of the transmission, and we are stepping up the voltage to the very high voltage level. That is what sometimes we may go with the extra high voltage or ultra high voltage. Then we transmit over long distances, right? This is what the transmission grid and the transmission line. And we have further the distribution transformer, and we step up according to the need of any industry consumers or the domestic consumers, right? Of course, we are end users, right? And understanding here and how the hierarchy would be, of course, and here the power level is even in the order of megawatts, and having the voltage in the order of kilovolt and the kiloamps, and then the distribution level power would be in terms of kilowatts, and the voltage would be very low, and even the current would be much high. Right. So understanding here, of course, as we are elevating the voltage here and we are reducing the voltage level. So according to the user need, we are able to change the voltages. So it means we are regulating the voltage, right? Not only for the user need, also to regulate the power flow between the power generating plant and the user. We have a mechanism to regulate the voltage. But here there won't be no mechanism of regulating the frequency. That has happened only in the generating power plant by simply changing or simply regulating the input fuel that is being given to the generator. That is what we use as a governor mechanism. With the help of this governor mechanism, and we are able to regulate the fuel input to the generator, the mechanical power, so that we are able to control the output electrical power in terms of voltage and frequency. So for controlling the output voltage of the generator, and we use an excitation system by changing the excitation current, and we are able to change the output voltage of the generator, or whereas changing the input power to the generator by changing or regulating the mechanical power input in terms of torque and speed, we are able to regulate the frequency. So of course the frequency of power generation is well synchronized with the turbine speed. This is what this generator is called as a synchronous generator, right? So the frequency regulation is possible here in the synchronous generator and in the power plant itself, whereas the voltage control is possible both in the generator power plant as well as in the transmission as well as the distribution system, right? As we use, just to recall the fundamentals on the electrical power system in terms of generation, transmission, distribution, we use a three-phase generator called the synchronous generators. And the transmission would be either in the form of DC, that may be, of course, high voltage or extra high voltage, or maybe in the high voltage AC transmission. And further, we have a three-phase AC system. It's very predominantly used across the globe. Maybe a transmission with a high voltage, overhead lines, or the cables, or distribution may be low voltages, overhead lines, sometimes cable, according to the nature of the location, right? And this is what, and the single line diagram, right? So now, coming to the importance of the power system, that the voltage and frequencies are the key quantities that governs power system security and power system reliability. Yes, as I said in the last session, power system security is governed by a frequency of the utility grid, and the power system reliability is governed by voltage of the utility grid. Of course, these two quantities govern the power system reliability and the power system security. So we are in a position to regulate both the voltage as well as frequency at every instant, so that you make the equilibrium between the source and the demand, right? This is what, as I said, this power system, classical power system, is well dominated by a large synchronous generator. Of course, frequency is a global variable linked to the equilibrium between the load and the generation, whereas the voltage is a local variable. Right, because the generation, when the generation is higher than the load, I mean, when the source power is more than the demand, of course, the frequency increases. If the generation is less than the demand, of course, frequency decreases. I mean, if the demand increases, frequency decreases. If the demand decreases, frequency increases. Of course, there always we have a rate of change of frequency. Of course, frequency is a quantity that can be changed at any time. Of course, it's an instantaneous quantity. So the rate of change of frequency that governs or regulated by a generator speed, that depends on overall system inertia, right? That is what, for any lower inertia system, the faster change would be there, right? Right, but this is not the case in modern power system or the renewable power generation system, that the renewable power generation systems are basically dump generators. We call it as they're fragile generators, right? So they don't provide any inertia. So according to the load demand and maintaining the frequency is a challenging task. That is what we inherently generate the inertia with the help of virtual inertia concept. By incorporating energy storage in the modern power system, we are able to maintain the grid as well as grid frequency as well as voltage stability. Right. That is what I told you, that in modern and future power systems are completely dominated by power electrons. Of course, they call it as inverter dominated resources. That is called IDR. Right. It meant that the power system is completely dominated by power electronics. It means that the inverter output frequency it is synchronized with the utility grid frequency. So it meant the frequency of the inverter can be defined and programmed in the converters. Of course, it has not a physical meaning. Understanding that the output frequency is produced according to the nature of the pulse width modulation, that frequency should be well synchronized with the utility grid frequency. Then only you are able to synchronize the solar photovoltaic or any renewable power generation system with the utility grid. So here the frequency is being programmed in the form of inverter output frequency by changing the pulse width modulation. Right. Of course, it don't have any physical meaning here. This is what now the inverter based resources, we call it as IBR in modern power system, that we uses the concept what is called the inverter based resources called IBR. Right, our power electronics dominated power system. Right, as according to that, the inverter voltage is being controlled and to be matched with the utility grid. Of course, voltage is a local variable that depends on the power flows and the power plant control. Right, so voltage is a local variable, whereas the frequency is a global variable. Right, and this is what the classical grid layout and understanding that having a different power plant that will interconnected through the grid and having different bus mechanism. As here, this is what the arrow indicate the load, and then the generators are well interconnected. Right, of course, this is the interconnected power system, and understanding the different power system characteristics in terms of frequency and the voltage level. Of course, the frequency is maybe 50 hertz or maybe 60 hertz. Other may not be in India and the European countries, and we follow 50 hertz 3-phase AC system, whereas in US and Canada they follow 60 hertz AC system. But still the frequency is still we use the DC. Maybe the transmission is possible with the DC using HVDC, but generation may not be DC. But the slowly the trend is getting changed. As I told you that yesterday, the DC renewable energy sources are very prominent in the today's power system. As solar photovoltaic is a source of DC power, and the fuel cell is a source of DC power. The battery stores DC. So eventually, the power plant we may use in future power system with the DC sources as well. But that may be having a limitation on the level of the voltage and what we generate, right? And understanding the normalized voltages in the transmission, generation, distribution, maybe in the order of kV, and other voltages level at 25 or 110 kV. Of course, the transport is well, it's measured connection, and whereas the distribution is measured at radial. Sometimes the transport may be interconnected, right? And this is what the level of voltages in the 3-phase AC systems. And as there would be a transformation from the today's electricity to the tomorrow's choice, and having well interconnected power system, as I said yesterday, as of course we need grid modernization and to cope up with adding what is called renewable energy sources along with the existing conventional power plant. Right now. Now understanding in power system that as being a generation, transmission, and distribution. So how the concepts are being evolved in today's power system. Of course, you can understand the classical system, primary energy source to mechanical energy. Of course, we use a steam turbine or a hydro turbine. Basically, they're the generators. And the electromechanical energy conversion, we use a generator, particularly synchronous generator. Of course, G, it meant for generator. And we have a transformer for stepping up the voltage in the transmission line or maybe in the transmission grid. Of course, it's a part of transmission. And we are further stepping up the voltage in the substation. Of course, that include both transmission and distribution. We have a distribution grid with the distribution transformer and a user, basically distribution, right? Now, in the new concepts in modern power system, the classical energy source or primary energy source are being replaced with the distributed generation. Of course, it is with the G become DG. So a distributed generation means renewable power generation system combined with energy storage. Right, and the transmission line has become a part of the microgrid. Right, microgrid means having again a distributed generation, and even the local load may not depends on the grid power. Still, that depends on the renewable energy source. So there would be a viability of microgrid, and there is a non-conventional power generation. Of course, there the generation unit. Right. Further, the transmission is with a flexible AC transmission system, and here, whereas the conventional, the transformer based transmission line, we have a step up transformer in the sending end and a step down transformer in the receiving end. Here the power flow is very unique and automatic control with the help of FACTS mechanism in the transmission. We have transmission further with HVDC as well. And in addition to that, we have energy storage in the receiving station, so that this may be installed either in the power plant, generating station, or transmission, or the distribution. Of course, it is associated with the generation, transmission, and distribution. Of course, the consumers are becoming prosumers in the distribution side. Yes. Now, of course, how the power system is evolved, understanding the difference between classical and the new concept. Now, come to the point of grid connection requirement, how this has been evolved in the classical power system. Understanding that, as I told you, the two key variables are very important that governs power system stability, power system security and reliability, are the voltage and the frequency. Right. So, frequency regulation is possible by regulating the active power. That is what we always make an equilibrium between the supply power and the demand power. And so we are able to regulate the frequency, whereas the voltage regulation is that meant reactive power control. So that is what wherever we concern about active power control, that meant frequency regulation mechanism, whereas the active power control that meant voltage regulation mechanism. So how this has happened in the conventional power plant, as we are able to regulate the frequency by regulating the active power in the power plant itself. That, as for example, as we have a boiler with a turbine, of course it is a steam turbine. As the energy is from the chemical, then that is being converted into mechanical with the help of boiler with the turbine. So that is steam to thermal and thermal to mechanical. So now we have a mechanical power that is being given to the generator. Right. Now, as I said, the frequency regulation is possible by regulating a mechanical input power that is being given to the generator. Right. So we sense the mechanical power. And so the mechanical power in terms of the speed, then that is regulated, that can be regulated with the help of governor mechanism by setting up the point in the turbine speed. So we are well regulating the frequency by the mechanism of governor, right? So that we are able to regulate the frequency, that is the electrical power output of the generator, and further we are transmitting over long distances, and further the load that uses the energy with the different form in terms of thermal, mechanical, and chemical, and the light energy as well. So the frequency regulation is possible by having governor mechanism in the power plant, whereas the voltage regulation is possible by injecting necessary reactive power according to the voltage at the utility grid. So we incorporate reactive power compensator or maybe voltage regulators. That is also possible in the power plant. So we change the excitation. Maybe with the help of a solid state excitation, so we are able to regulate the generated voltage further by incorporating like a tap changing transformers or maybe any factor device, or we are able to regulate the voltage through the power system, either maybe in generation, transmission, and distribution. Right. So this is what I told you, the conceptual regulation of the conventional power plant for both the frequency as well as voltage. So here the output voltage is being controlled with the help of the voltage regulator through the exciter. That the voltage regulator usually, it compares the voltage reference voltage along with the actual voltage that is sensor by the voltage sensor, then that error is being given to the exciter. So according to the value of the error, then the exciter that excites or change the excitation current that is being given to the field winding of the generator. So by changing the excitation current, we are able to change the output voltage of the generator. This is the way we are able to regulate the voltage in the power plant itself. Right. And whereas in the turbine side, how we are able to regulate the frequency, this frequency regulation is possible by controlling the mechanical power that is being given to the generator. So it means we are sensing the speed of the turbine, then we are setting the speed reference, then the error is being given to the governor. And of course, the governor, they take action to regulate the fuel input, right, via one servo motor, so that this feedback is given to the governor according to the position. So we are able to regulate the input fuel, that is a steam that is being given to the turbine, so that it is well regulating the mechanical output of the turbine. So by regulating the mechanical power output, you are able to maintain the frequency constant from the generator side. This is the way the centralized power plant, they're able to control both the voltage as well as the frequency. So we don't face any difficulty in power system reliability or the security. That may be the case of the problem. There is a concern about the stability or the security when the grid is under abnormal condition. Maybe the grid faces the difficulty because of there would be a symmetrical or unsymmetrical fault occurs in the system. That may be the worst case. But during steady state, conventional power plant or centralized power system don't face any difficulty in voltage stability or the frequency stability. This is what, how could you emulate these characteristics in the modern power system? Now we are in the 21st century, and what is our concern, and what is the role of a modern power engineer? What is the role of a smart grid personnel? So it meant, how could you emulate a modern power system characteristics at par with conventional power system characteristics? It is not at all possible. This is why conventional power plant, we have a turbine-based generator. Of course, it has a rotating mass. It have a huge inertia that will damp out any oscillation, that will damp out any internal or external disturbances. It is able to cope up with the sudden change in voltage of the frequency. They will regulate the frequency of the voltage. So you don't face any difficulty of the grid stability. But that is not the case today. Why? As we have a grid that is connected with the kind of EV charging stations, and it's connected with the renewable energy. Basically, they are the variable power sources, and maintaining the characteristics of the modern power system or renewable power system at par with the conventional power system is a very challenging task. This is what we are revisiting the requirements of grid connection requirements of renewable power generation system. Right. Now, how would you emulate the performance mean? Of course, regulating the voltage and frequency. Right. As I told you, frequency regulation is nothing but active power regulation, and voltage regulation is nothing but reactive power regulations. Of course, we are going to maintain the equilibrium. The equilibrium between the supply and demand, either in terms of active or reactive power. Right. Now, you can see that what has happened when the frequency may decrease or when the frequency may increases. Right now, the frequency may decrease or increase according to the load demand. Right. For example, the demand is more than the source power. Of course, it causes frequency down. Right, that is what. So now you can understand that page generator or a conventional generator or variable generator or any resource, so that may cause the frequency down because this power is very stagnant. Sometimes that may happen when the load demand reduces. The load is base load, that is not a peak load. Maybe adjustable load and variable load, or maybe the minimum power loss. It may cause a frequency up. Frequency up, it meant decreasing the demand. Frequency down, that meant increasing demand. Of course, then you have to maintain an equilibrium, right, between the supply and demand. Mean how the real power can be well regulated. That is what. Sometimes to maintain the balance between the frequency up and the frequency down, we incorporate energy storage device. So by incorporating renewable energy storage or energy storage, it is able to maintain the supply demand mismatch, so that the grid is always in the equilibrium condition. So you are well regulating the frequency. Right. Now come to the point in the voltage regulation. Of course, the voltage regulation is nothing but a reactive power compensation, and how the compensation maybe whenever the voltage down. right? Maybe when the load is suddenly increased, right? There would be a dip in the voltage at the point of common coupling. So it means the grid, it needs the source of reactive power, right? As you can use the line capacitors or maybe a switched capacitors or synchronous generators of the condensers, you're able to maintain the voltage profile, right? At power with the actual grid voltage, or sometimes the voltage may down, right, because of the line inductance or maybe inductive load or maybe induction generators and the motors. They require reactive power from the grid, so they draws more reactive power eventually the voltage. This is what we need sometimes, reactive power compensation, because solar photovoltaic or wind energy conversion system, your generator do not support any reactive power, right? That is what we use as energy storage devices for the support of both active as well as reactive power in the today's power system, right? Now come to the point in the frequency control. As I said, it's maintaining the equilibrium between the generation and demand. As we are able to maintain the frequency constant, of course, it accompanies the energy exchange agreement neighboring area, still keep enough energy reserve. That is what we use as energy storage. Right. Now, understanding the frequency response, and if there would be a power imbalance, right, maybe due to loss of synchronism, maybe due to load connection. Now, the frequency may decrease or increase beyond its threshold, right? So, the threshold is 50 or 60 hertz. Of course, as you maintain the standard limit in the 50 hertz, but sometimes it may cause a deep reduction in the frequencies due to sudden increase in load or maybe due to power imbalance. But you have to bring back the frequency to the actual value. So how how would you make the frequency reserve so that it is able to maintain the equilibrium condition, and what would be the response time? This is what, and this shows the steady state limit of the frequency variation. This is the instantaneous limit how it could maintain. If the frequency suddenly decreases, then of course you need to have an inertia reserve or fast frequency reserve. All right, so you may use a kind of energy storage that immediately supplies the power according to the load demand, so that you are bring back the frequency to the original value. Right, this is what immediately you are supplying necessary active power by auxiliary source or maybe having inertial reserve. Right, then further what you are doing, you are trying to curtailing the reserve of the frequency. It increases, having the time period in terms of seconds. And after this level, as once you reach the steady state, further the frequency may go to reach the threshold or the standard level of the frequency. That is what is called frequency restoration reserve. This is the time period. And once the frequency is about to reach is the actual value above the standard limit, then you are replacing the reserve. You may cut out this source. This is the way you are able to maintain the frequency from between, you are able to maintain the frequency 50 hertz or 60 hertz, right? And as I told you that the frequency response, how the response time, it is very important. So this response time is good in conventional power plant, as we have an inertia reserve with the help of synchronous generator. And also we use certain mechanism of storing a mechanical energy by using flywheel energy storage as well, right? This is what, or sometimes like a pumped storage power plant, as we use as an backup by having pumped storage power plant with the slip power recovery scheme. So we may supply necessary reserve with the help of that, and we are able to maintain the frequency, right? But however, what would be the activation time as well as the activation time of the frequency restoration, that it makes sense the response of the frequency regulation. Right, now understanding the general characteristics of the frequency support services, maybe typically in Europe, I could refer a paper from the author from Spain, and I could understand that what would be the initial reserve frequency curtailment and the frequency restoration and replacement reserve. You understand that, and the type of activation is, of course, it's an automatic, somewhere in the frequency restoration manual, because it's about to reach the steady state. Of course, the activation time may be minute, even sometimes that may not require, because as long as the frequency is constant, you no need to worry about it, right? And it maintains the well synchronism. But here, when the frequency is down, right, then beyond the threshold, of course, and now you understand that, for example, a non-synchronous generator means you should procure the inertial reserve. This is what we use as energy storage devices, so that it supports necessary. Here we use the energy storage that supply a huge amount of power according to the load demand. Of course, the activation time should be less than 1 or 2 seconds. Right, of course, here the activation time, once it is the frequency is restored, then acceleration time may be second. This is what sometimes we use the kinetic energy from the rotating mass, right? The provision for synchronous generator. But in the renewable energy, we don't have any kinetic energy because solar photovoltaic is a very dumb generator, right? It uses simple semiconductor. It's a static device, right? That is what you don't have any rotating mass. The problem may arise when there would be a sudden increase in load or sudden increase in demand. This is what we face difficulty in the grid. That is what now the grid is very weak, and there would be a problem of grid stability in today's or modern power system. All right, and however, the frequency containment reserve may use a governor mechanism because once it is able to reach the steady state, here the period may be in seconds, less than 30 seconds, but still you use a governor, right? That is called a power frequency droop control. You are able to regulate the frequency. Further, it may reach the steady state, so the response time let it be minutes, so that you are able to maintain the synchronism. Right, and yes, further as understanding and in the grid code requirements, what need to be controlled. As I said, in the grid code requirements, as imposed by power system operators, that the power plant must accomplish to be connected while selling energy to the grid. Of course, the frequency and the voltage support. Of course, the power plants are required to contribute for the voltage support with the help of reactive power and the frequency support with the help of active power. Right. Active power control, as I told you, that the power plants can be demanded to curtail or control the active power to given set point. And reactive power control is possible by using regulating the voltage or having kind of reactive power compensator as well. Right. And in addition to that, the grid connection requirements that also include low or high voltage right through. This may be the possible when the grid faces the difficulty during fault. Right. Of course, when fault occurs in the grid, the power plants need to be connected with a utility grid, even when there would be a large voltage deviation during the fault. This is what the low and high voltage right through. It means when there would be a low voltage, when there would be an unsymmetrical fault, maybe about 20% of voltage deviation from the actual, but still the power plant remains connected with the utility grid to maintain the continuity of the service. This is what is called a low voltage right through. Sometimes maybe a sudden change in voltage, or maybe whenever there would be an islanding in the grid wherever we have a kind of wind form, the sudden islanding that may cause us the increase in voltage during the condition as well. So the power plant need to be remain connected with the utility grid to maintain the continuity. These requirements are called low and high voltage right through requirement, especially for wind turbine system and solar photovoltaic as well. And we have sometimes ramp control that we need some kind of control according to the rate of change of frequency. There is a power plant need to limit the rate of change of power injected to the network, especially relevant to PV power plant. So we invariably require energy storage unit. And in addition to that, the renewable energy or the solar photovoltaic that requires inertia emulation, because solar photovoltaic do not have any inertia. They are the zero inertia responses. That is what we use a power electronics based power plant that can be demanded to emulate the inertia of the synchronous generator. Right. That is a way now we are able to maintain the grid stability by emulating its inertia with the help of inverter. That is what we use as nowadays, the inverter operation that is being connected with the utility grid and the renewable energy. According to the mode, they call it as the grid forming inverter and the grid forming inverter. You know, the grid forming inverter is one of the emerging techniques so that it is able to provide the necessary inertia to maintain the grid support and maintain the grid stability as well. Right, and the black start it's another important thing that sometimes when the fault occurs and the fault is quite severe, sometimes there would be a blackout, there would be a large shutdown. So still sometimes the power plants are required to restore the system voltage and frequency. So to contribute to restart the system after blackout, that is what is called a black start. Sometimes, as I told you, that we may have a kind of inverter that acts as a grid forming inverter. So it means the grid forming inverter that supports the utility grid when the grid is under fault condition. Right. That is what sometimes the inverter that acts as a solid state synchronizer. I mean, the power plant can be required to contribute to control the system synchronization, but not synchronizing the inverter with the existing grid. But imposing and creating a grid, this requirement is increasingly important for power system dominated by converters. So it means the grid power voltage source inverter that is being connected with the utility grid that virtually act as a solid state synchronizer. So as maintaining the inverter output frequency and the utility grid, we are able to maintain the synchronizer. That is what the mode and the operation is being called as a grid forming inverter, or we call it as GFO, right? And in addition to that, sometimes the power plant can be required to damp out any oscillation. As I told you, they don't have any inertia. Of course, it needs sometimes the support of the reactive, power system oscillation, adjusting active and reactive power injection. Invariably, it requires kind of a damping mechanism with external filters and the inverter, right? And I told you that the reactive power control is essential for voltage regulation. So how the reactive power is being provided? Maybe as is the inverter, that's a source of reactive power, having the DC link voltage with the capacitor, or maybe a battery, and other devices like ultra capacitors or synchronous condenser or FACS devices or the transformer regulation. You are able to provide necessary reactive power to the utility grid so that you are able to maintain the voltage at the point of common coupling. All right. The relevant methods, that basically the relevant methods or modes are reactive power control mode, or AC voltage control mode, or in some sense we may call it as a power factor control as well. These all make sense in controlling the grid voltage. Right. Now, understanding the voltage control, as you the rate of change of voltage that trigger the rate of change of reactive power. Right. So when the change of voltage as the voltage it's in the negative signs, and how the reactive power is being injected in the negative. That is what the grid requires leading reactive power whenever approved decrease in the voltage. And whenever approved increase in voltage, then it needs to absorb the reactive power. That is what, right? So, but however, we make certain threshold in the changing voltage level, it should be about 5% the threshold value, and you are able to maintain. But when the voltage deviates from the threshold, it may absorb reactive power or it may supply reactive power. That is what the additional reactive power demand requested to the either wind power plant or maybe solar photovoltaic. That is based on the voltage levels that varies between that varies beyond the threshold level. Right. This is what is called the VQ grouping characteristics. Right. And according to the grid code defined for this reactive power and the voltage, you understand that as once you are maintaining once you are maintaining the equilibrium, of course, if the voltage level is at a high, of course, the power factor is unity power factor around 0.95. But whenever the deviation of the voltage between 0.005 and 0.005 in X and Y axis, now what has happened? How the active power is being adjusted in addition to reactive power. Now, understanding that once the active power is at unity and it's well maintained and doesn't require any reactive power support as well as the power factor improvement. But whenever there will be deviation in the voltage, it needs the support of reactive power in addition to power factor improvement. Right. This is what the grouping characteristics between the active and the reactive power characteristic curve and how the changes would be. All right. And in addition to that, we may have a voltage power factor curve, that voltage limit depending on the power factor. And all of us know that. And all of us know that the power factor that decides the voltage, if the power factor is very low in the utility grid, eventually the voltage degrades. Right. This is what, once the power factor is being made 1, unity power factor of the voltage is in the nominal value. Right. Whenever the voltage, the power factor decreases, you understand that there will be a decrease in the voltage. Right. So for voltage, power factor is being reduces. It is less means, of course, as the power factor reduces, the voltage decreases. But on the other hand, if the voltage is, if the power factor is about 0.925, you see the changes in the voltage. Of course, it reduces less than 0.95. It needs leading reactive power. So it means it needs the power factor improvement. That is what we use over excitation, so that it is able to bring back the power factor to unity. Similarly, under this side, if there would be an under excitation, if the power factor is less than 0.95, of course, it absorbs reactive power. That is what the power factor becomes negative. It meant lagging power factor. So, but again, you bring back the power factor to the actual unity power factor, meaning, of course, this side as you use the under excitation, but invariably you bring back the power factor to the unity so that you are able to maintain the voltage profile constant. Right. This is what the active power management in the renewable power plant. We may use the mode to maintain the power balance. Maybe during normal, we may use maximum power point extraction. The balanced control mean when the actual and the delivered power, the both has to be well balanced. This is what's called a balanced control to limit a constant value of the active power. Sometimes, according to the changes in the demand, right? According to the changes in the demand, according to the changes in the demand, the load power, available power follows the same, same response. This is what is called the delta control. So it means reduction of power generation if the load demand reduces. But mostly we don't go with the delta control, that as the demand less and we are reducing the supply, right? But sometimes we may make a kind of resource in the power plant. If the load demand reduces, but still the surplus amount of power may be stored with the help of energy storage device. So that may be used when the demand is more than the supply, right? This is what the ramp control, where whenever there will be a sudden change in the active power, of course, the delivered power it exactly follows the reference trajectory of the available power. This control is very essential to maintain the grid stability. Whenever there would be an abrupt change in active power because of changes in the load demand, right? This control is what is called the ramp control. And sometimes the frequency response is quite difficult in solar power plant because no available inertia. That is what, so we invariably uses energy storage devices. There may be problem with the over frequency because this may happen whenever you could follow, whenever you could follow the demand is quite lesser than the solar photovoltaic, or the solar photovoltaic is able to produce more power because of that may cause over frequency event because of the maximum power point tracking. Right, sometimes we use energy storage to store the surplus amount of energy. Right, under frequency even this may be possible when the power demand is more than the solar power available. This is what most of the cases we face. Of course, the deloading is possible. Deloading means in order to meet the load demand, sometimes we may reduce. In order to meet the source power, sometimes we may reduce the load power. That is what we follow the technique, what is called load shedding. So that is a way we are able to maintain the frequency constant during under frequency. This is what is called a deloading operation, but still the problem of uninterrupted power at the particular zone, or still we use energy storage to cope up with under frequency event, so that you are able to maintain the equilibrium between the available power as well as the deliverable power, right? So sometimes the deloading operation, it can use power reserve for under frequency. Sometimes we use frequency supporting services. Or sometimes the disadvantages is that sometimes it reduces the income from the power generation, and because we have less source of power from the solar photovoltaic, it may not be able to meet the demand. This is what it may reduce the income from the power plant, right? So then what can be done for the frequency response? Use a droop control mechanism. So what is a droop control mechanism? According to the changes in the frequency, you are able to regulate the required power. That is what the reference power you are going to regulate by comparing the actual and the reference frequency as that is given to the frequency deadband. Yes. Now, what would be the frequency response, or what would be the changes in the frequencies acceptable level? That may be between 49.5 to 50.2. So when the frequency goes below 49.5, that seems to be like under frequency. When the frequency goes above 50.2, that seems to be like over frequency. So always you make the threshold for the change in frequency, and then you are able to maintain the active power balance, right? And sometimes this may be possible with the manual active power dispatch, so to maintain the frequency constant. And this is what the regulating mechanism of the active power by comparing actual and reference frequency. Here you understand that the active power output, how you could will map up with the frequency. When the frequency is at the 50 hertz, of course the power flow is very nominal. It is the the actual power is about 1 per unit. Of course, sometimes if the frequency goes below 50, right? So ultimately, and now what happened? And now the demand, the supply power is more than the demand. That is what the frequency. Sorry, when the frequency is increases from 50 to 50, mean it's over frequency, because the active power output it reduces. That is what the frequency increases. Because the demand is less, but active power demand reduces. Now you come to this point. Now what happened at this frequency, the stable operating frequency at the stable operating power of 1 per unit. Now the frequency may reduce as 47 mean. Then now what happened? Frequency may reduce mean when the demand is very high. That is what, in order to cope up with that mechanism, we use energy storage devices. So always you maintain the deadband between the B and C so that you are able to maintain the frequency corresponding to the active power regulations. Sometimes over and under frequency event may be made it with inverter switching, or sometimes maybe possible if the frequency is beyond the limit. We are able to de-energize the inverter so that the inverter may be disconnected from the utility grid. That is also possible when the under frequency events happens, right? And active power variation, as I told you, that the frequency variation between 50 and 52 mean how would you able to apply a governor control so that you are able to maintain the frequency in 50 hertz. So now the frequency is at 50 hertz and you are able to maintain the actual mechanical power. Whenever the frequency is going, it's increasing means, so for every changes in the frequency of 1 hertz, we have to regulate 0.4% of the actual mechanical power so that you are able to maintain the active power regulations along with the actual mechanical power so that the frequency of the utility grid or the generation, it remains constant. Right, but only the problem with the over frequency even that may happen when we use the synchronous generator under over excitation, whereas the load demand is quite stagnant or may reduce. Right. So now, in addition to that, understanding active and reactive power control with the help of different mechanisms, sometimes we need to have a robust response when there would be a sudden change. We invariably use inertia emulation technique. What is inertia emulation? Because your ultimate aim is to regulate the frequency in order to regulate the active power balance, right? So it means inertia emulation or synthetic inertia. How would you make it? Now you understand the frequency the actual setting frequency that the error is being given to the change in the frequency of the deadband. You are able to generate the active power reference. So it meant. So this mechanism has to have to satisfy the swing equation so that the grid is always stable. It maintains the frequency stability. This is what a synthetic inertia mechanism. So inertial response can be achieved proposing additional control scheme that affect the generated active power in the presence of frequency deviation, so that it allows the behavior similar to synchronized generating unit in this situation. Then what can be done? You have to use the controller in addition to the energy storage. There is a way you are able to maintain the active power balance so that the frequency remain constant. Right. And the fault right through, as I told you, that when the grid faces the difficulty of the fault that may cause the low voltage. So even at the low voltage, still the renewable energy source that maintain or that remain the energy that is remains stored in the utility grid, that operation is what is called a low voltage right throw, and that the fault throw right throw requirement is very important on changing the voltage level from 100% to 15%. How you would be able to maintain the nominal voltage at least above 90%. So how the response time would be. This is what for the different grid code and different countries how they could maintain the fault right through requirement. This was just extracted from one of the review paper in IIT renewable power generations. All right. So overall, as understanding that the power system is experiencing a deep transformation, right, from classical power system into modern power system, as making the sense of a very smart system or the smart grid, right, there would be a massive penetration of renewable energy sources, particularly photovoltaic wind. They are large scale power generation unit. They generate power in terms of megawatt level. There has raised the concern of the system operators, and they call it as the grid connection requirements. And the PV power plant are not required only generate the power when the resource is available. They have to be operated as a power plant supporting the entire power system. Right. And the system support main requirements include voltage support, active and reactive power management, frequency support, inertia emulation, fault right through requirement, grid synchronization, power factor improvement. These all the power factor maintenance is all, of course, it's coming under grid connection requirements. Very important thing in a modern power system, having grid connected solar photovoltaic or inverter based resources, maintaining the power factor of the utility grid. The requirement says even at 50% of load that is being connected at the point of common coupling, the grid ensures the power factor at least 0.9 lagging. It's a very, very important requirement while you integrate solar photovoltaic or wind turbine system with the utility grid. Right. Now let us come to another point is a grid connection requirement. In addition to the standard, what are the standards usually we follows for integrated solar photovoltaic with the utility grid? Of course, the second stand, the ensuring the power quality or ensuring the sinusoidal current injection into the utility grid, we follow the requirement in terms of power quality. So that meant the quality of the power mean quality of the voltage and current waveform, right? Usually, understanding that normally the maximum voltage total harmonic distortion, what is called the THD of the grid voltage, should be within 5%, and the maximum individual frequency voltage harmonic, it is less than 3% of the fundamental. This is the very minimum requirement while integrating solar photovoltaic with the utility grid. Of course, the current that is being injected into the utility grid should have a THD of less than 5% of our total harmonic, and whereas the individual harmonic should be less than 3%. Right, and understanding that, and however, as we are making the as we follow the total demand distortion, sometimes for the distributed generation, the total harmonic current distortion in percentage of maximum demand load current shall be less than 5%. This is what we follow. So this standard is particularly provided by IEEE standard, that is IEEE 519/1992, provides a detailed specification on the maximum individual harmonic current distortion, the percentage of maximum fundamental load current. That is summarized here for individual harmonic orders. Of course, it ensures the THD should be less than 5%. But even harmonics are limited to 25% of total harmonics. But most widely, the inverter output voltage waveform is of half-wave symmetric. It do not inject any even harmonic components. Right, only they inject the order harmonics, particularly third harmonic, fifth harmonic, seventh, ninth harmonic, 11th, up to 25th harmonic. Now the order has gone more than 25th in the modern power system. That may go up to 35th order. Now further in the updated IEEE standard, that has been made up to 65th order. From 35th to 65th order, they call it as the supraharmonics. Right, these are all the standards, the power quality standards, IEEE standard, IEEE 519 standard, that is established in 1981. Every year they used to revise. Now we have a standard IEEE 519 2014 standard. That is what the updated standards currently available in the IEEE and IEC 61000 series. It meant for the industrial power system. Right, and this is followed by the European Commission, European countries, and IEEE 1531 is issued in 2003 for the shunt active harmonic filters for the design, and IEEE 929 2014 standard. It is meant for IEEE recommended practice for utility interface of photovoltaic power system. It is issued in 2010, but still last year they have updated the requirements. And further, there's a standard. It's a US-based standard called American National Standard Institution called ANSI. That meant for electrical power system and equipment voltage rating, that is issued in 1995. This also include a selection and standards for induction motors as well for industrial automation purposes. This is the way we classify induction motors with the different classes called class A, class B, class C as well, according to the given nature of the insulation as well as given nature of the energy efficiency. Right, interconnection standard. These are the interconnection standard for solar photovoltaic, and this has been given here for all the requirement. But go through it and you understand very clearly about the recommended practice for utility interface of photovoltaic. Of course, here it provides an excellent primer. It provides an excellent information for PV inverter interconnection issues, and this was developed. It is available in IEEE Explore as well. And why we need PV interconnection standard? Because many times we have a kind of industry equipment with rotating machinery, and sometimes we have the interconnection requirements in different countries having many requirements. Of course, we need to ensure the standard so that we are able to interconnect. And this is the IEEE 929 standard that meant for the personal safety, equipment protection, and power quality and utility system operation. Of course, it addresses only the interconnection equipment requirements. And IEEE 929 reality, what it impact that once the utility system is being connected with the utility grid, PV via inverter. So how would you make an interconnection between the PV array and the utility system? This is what it meant, and that include different power quality norms. Of course, these power quality problems usually arises in the utility grid because of a proliferation of nonlinear load. As we connect at the point of common coupling, of course, all customers will suffer because there would be deviation in the actual system voltage. Right. So PV should not add to the problem, but still the nature of the loads are all nonlinear electronic loads. For an example, that addresses the service voltage flicker, the frequency, waveform disturbance, and the power factor, voltage sag, and different like transients. These all, of course, it's a part of the power quality. And of course, the safety and the protection standard according to IEEE 929/2000, that is responsible for the abnormal utility condition, maybe voltage disturbances and the frequency disturbances, or islanding and reconnect after the utility disturbances. So these standards are well articulated in the safety and the protection function. And direct current isolation is very essential, because if the direct current is not being isolated between the solar portable and the utility, inherently they generate odd harmonics, even harmonics. And of course, they causes double frequency oscillation that may damage your DC link capacitor. Of course, the DC link or direct current isolation is very essential in interconnecting solar photovoltaic with the utility ground. There is a mechanism of grounding, and that include manual disconnect. And this is the IEEE 929/2000 standard according to the abnormal utility grid condition. What will be the tripping time according to the voltage level? This most widely we follow the system according to the level of the voltage variations and how many cycles it take to trip or to seize the inverter from the operations, right? And this is what the manual disconnection of the inverter when there would be sudden deviation in the voltage level, right? And in order to ensure the safe operation of the inverter, because at any cost, the inverter should not be overloaded, right? Even should not cause any over voltage as well, because they are very sensitive in any kind of over current or over voltage phenomena, because inverters are made up of simple semiconductor devices. They are prone to damage because of excessive voltage and excessive current. That is why we have a protective mechanism of the power electronic switches as well against over voltage and over current. And this is the annexes are available in terms of annexer A, annexer B up to annexer G. You understand the different the sections are available with different annexes. And this is standard for IEEE 1547/2003 standard for interconnecting distributed resources with the electrical power system. And you understand that while interconnecting with the load with the distributed energy resources like DER 1, 2, 3, and they are well connected with the point of common coupling. So how would you make the interconnection terms and the standard, right? This is available here in terms of different testing requirements. And this is the IEEE P 1547 standard that meant for verifying the test procedure and order, but does not define a comprehensive certification process for interconnecting distributed energy resources with the electric power system. And this is the purpose of 1547 that mentioned to establish or to make any kind of flexibility or connection requirements. And this is a 15472, what it meant that is available. This is all the 1547 standard that meant for interconnecting distributed energy resources, right? And this is 15472 that meant for providing the technical background application details and for providing various forms of distributed resources technology and interconnection issues and the technical requirements for operation and presenting good practices approaches. And the 1547.3 that drafted that for monitoring information exchange and control of distributed energy resources interconnected with the existing power system. This is UL 1747. It is standard for the inverters and the converters and controller for using independent power system, right? Especially for a renewable power generation system, and that addresses the electric shock hazard and fire hazard and the safety mechanical hazard and the utility compatibility interconnection for grid-tied applications. It is well articulated in UL 1747. And of course, we have that the utility compatibility interconnection concern, and mainly they are concerned about the utility operating voltage and frequency parameter, islanding detection, and output power quality as well. Of course, as you know, very important thing in the solar photovoltaic wind power plant is what is called islanding. Because when the distributed energy resources continue to operate, when giving power to the grid, sometimes utility may not be available. Utility source is no longer present. That situation presents many hazards, including electric shock to the utility service personnel. The thing the side of the utility transmission line is electrically dead. This concept is what is called islanding. So how could you able to detect that islanding? How could you able to prevent the system against islanding? That is what we go with the different anti-islanding technique to ensure the safety operation. And the power quality, as I said, the utility interconnected DG products must meet a minimum output power quality requirements that include Output power factor. Yes, as I said, output power factor should be more than 0.85%. Even you connect 50% of the load. Of course, the harmonic discharge in terms of voltage current should be less than 5% of the THDR to full output power. However, the DC current injection should be less than 0.5% of rated output current. This requirement is very important while interconnecting solar photovoltaic with the utility grid via inverter, because inverter it has a DC source and the DC link. Of course, in addition to a sinusoidal component, sometimes due to the due to the pulse width modulation with the dead zero concept, sometimes it may inject what is called the DC current. Right. So this current should not exceed 0.5%. If not, then the DC current, it may adversely affect the distribution transformer performance because of because of the DC current, your transformer core may saturate, that may cause us increase in iron loss of the transformer. Eventually, the transformer would be deloaded. This is what the DC current injection must be less than 0.5% of rated output current of the inverter. So these are also an important requirement while interconnecting solar photovoltaic with the utility grid. Right, and this is UL 1747 expansion to cover all interconnection of the DGs that, of course, that include different energy sources like a photovoltaic, fuel cell, micro turbine, wind and hydro, and sometimes DG set as well. Right. So these are all the key references in drafting this particular presentation on the grid connection requirements of solar photovoltaic and the standard for solar photovoltaic power system. Right. And thank you very much for your kind attention. I have highlighted the importance on the grid connection requirement standards of solar photovoltaic power system. Of course, as one can understand the fundamental difference between the classical or conventional power system and the modern power system, how this renewable energy, it created an impact and also associated with the grid stability measurement, how the source of active and reactive power is essential to maintain the frequency stability as well as voltage stability. Right, so these all are very important things. In addition to that, we haven't, these standards are not yet updated according to the EV charging and EV charging stations, so how they poses the grid stability. Still, it is a challenging task. So far, we have discussed only on interconnection of solar photovoltaic with the utility grid. But when they say the grid is being connected with the EV vehicle for the charging, then still the grid faces instability. Right, adversely affect the performance of the grid. That is what still this all standard has to be revisited, that included EV charging infrastructure as well as stabilities. Right. With that, let me conclude my talk and thank you very much for your kind attention. And if you have any doubt, please let me know.